Now it shouldn't be as hard, actually, but at the time when I set up the test environment, a lot of features that I needed were not available in the software that you use to set up the test, to set up the publication point test environment. The options weren't there. And they introduced additional features actually after I did it. I think because I was needling the developers, like, how can I bypass this sort of security check because of the test environment and so on? And they eventually have also created the ability for people out of the box to set up a test environment now.
Welcome to the Head of the Breach podcast. I'm your host, Casey Kimler, where we talk everything offensive security. So, Donika, tell me a little bit about the Stellaris downgrade attack research that you did. But I read the paper, and there's a lot of basic understanding of BGP, RPKI, all the things that you need to, the groundwork that you need to understand first. So I want you to explain to our listeners the awesome research that you did, but go ahead and lay us the groundwork of like, what is BGP, what is RPKI, and then dive deep into what you discovered.
So BGP is one of the core protocols that makes the internet as we have it possible. It's a protocol that essentially allows for packets to get from point A to point B efficiently and fast enough. But BGP was developed decades ago at a time when the internet was much different from today, and the entry barrier to the internet was much higher. So very few entities were actually working with this new technology. So when BGP was created, things like efficiency and speed were of the primary importance, but not security. So it's a protocol that is not secure by design. And the result of that is that nowadays, this is a protocol that is not that does not fulfill the needs of modern internet. It does not provide security guarantees. As a matter of fact, BGP hijacking attacks are a major attack vector. They happen very often. They have extraordinary consequences, monetary, but also in terms of the availability of critical infrastructure. And we need some kind of tool, some kind of security wrapper around it. And that's where RPKI kicks in, essentially. What RPKI does is it provides these extra security features to BGP. And what it does is the following. Internet resources, IP addresses, they belong to some entity that has purchased them or has a license to use them for themselves. And all of these entities issue out a file, a ROA file, it's called, in which they say, this number of prefixes belongs to me, ASX, for example. And when the entities do that, they put them in some specialized repositories, which are called publication points. And now the other part of the RPKI infrastructure is the relaying part, which is the workhorse of RPKI. It picks up all of this data in these repositories, processes them, generates like the tuples, network prefix and legitimate owner, and then gives this information to the routers. So now a BGP router that receives an announcement is able to tell, hey, this announcement is correct because it matches with the data that I received from the relaying party, or this announcement is either a route leak or a hijacking attack because it doesn't match, it contradicts something that I have received. And this is essentially how RPKI would help BGP routers to bypass hijacking attacks or route leaks. So in our research, we were looking for what could potentially be some vulnerabilities in RPKI in this whole processing part. And we noticed a couple of things, and then the whole picture came together. So first of all, when the data from these repositories is processed, there's also the possibility for stale data to be there, for replay attacks to happen. Therefore, one component of this data is the manifest, which lists all the files that the relaying party is supposed to work with.
Real quick, Donika, that manifest file, is that housing like autonomous systems, those actual ASNs, or what is it? What does it actually contain?
What the autonomous system does is just create the mapping, prefix and ROA. Then the publication points have an inside logic of their own. So there is an RFC that dictates how a publication point is supposed to operate. You don't just dump their objects. They must have manifest, they must have certificates for the authorities that are allowed to issue this data. And the manifest is just a file that is automatically created by these customized publication points, customized repositories, in which the files and the hash of the files that are supposed to be the latest content of that repository are listed. Essentially, it tells the relaying party anything that's not in this list, you should not process it. Everything that is in this list is something that you need to work with. And that's essentially the manifest file, which usually, for some reason, okay, there is reason behind that. We want the manifest to be very fresh, but sometimes it is just very too short-lived. It can be a couple of hours. According to our measurements when we did the paper, maximum a day or 2 days lifetime, or not more than that. And this is a very exploitable cycle because there are some things in the way that RPKI works, in the way that the querying of these repositories work, in that you have to do it very often and periodically because this is a very dynamic system and content can change anytime. So you have to make sure that your data is fresh because your data is then going to feed the routers. So you have to do that very frequently. And the rule is after you've done all of the querying, after you finish querying everybody, then you generate that compact output that you send over to the router. And that's where the problem kicks in. What if this process lasts for a very long time? The whole querying every single repository out there and processing everything. What if it lasts for as long as a couple of manifests expire? And you can do the measurement very easily because this data is public. You can just download the files from repositories, see when they expire, and then time your attack accordingly. And that's essentially what we did. We actually did it in our isolated test bed, of course. We created publication point subtrees that were so large that you could stall the whole processing for up to 6-8 hours, even more if you wanted to. And at the same time, the system is relatively deterministic. So the query patterns are very regular. For example, Routinator, a very popular relaying party implementation, by default queries every 10 minutes. So you know essentially when a query is going to land, more or less. So what we did was we made the process last for a very long period of time. We knew more or less the query patterns for any relaying party out there. You could actually measure that. And we would rate limit the name servers that were responsible for the repositories in question. So if we wanted to make sure that the manifest expired, but we didn't want an update to take place during that particular period in time, we would rate limit either the publication point server or the name server as well. And we would make sure that the whole process would last for 10 hours, for example. The relay party never managed to contact the repository that we wanted to attack because the request was just dropped because we made sure to rate limit it with spoofed packets. And the result was, at the end, the data that is then sent over to the routers, the final data, doesn't contain certain mappings that we wanted to blind the routers from. And this opens up the possibility to launch a hijacking attacks against the resource that should have been protected. But it is actually possible to make sure that some resources don't get adequately passed over to the router. And some measurements that we did was, like I said, all these experiments were within an isolated test bed. We never attacked anyone, but we measured how many publication points or repositories out there would be vulnerable to this rate limiting. And we did find, I think it was, if I remember correctly, because the paper is a little old, like 47%, I think, of publication points were vulnerable to this kind of rate limiting. And we also did some disclosures to those we found could be potentially affected by Steloris. So the main problem that Steloris presents is the fact that you can do downgrade of RPKI protection for resources that should have been protected, and you can do that very silently because unless someone looks at the logs, they will never see that something is wrong. You have to continuously check how your relaying party is behaving because the relaying party doesn't crash. It doesn't throw any errors when you do this attack. It just continues work as usual. It signals nothing. So this is a major problem, that you can do this attack very silently and unless you dig deep into it, you can never find out that it ever happened.
That's interesting. But how hard was it to set up the test environment to actually test it out in your lab?
It was hard. Now it shouldn't be as hard, actually. But at the time when I set up the test environment, a lot of features that I needed were not available in the software that you use to set up the publication point test environment. The options weren't there. And they introduced additional features actually after I did it. I think because I was needling the developers, like, how can I bypass this sort of security check because of the test environment and so on? And they eventually have also created the ability for people out of the box to set up a test environment now. But at the time, it took me a month or two, actually.
So, I mean, you're setting up repositories and BGP routers, right? Or what does it look like?
So the problem was setting up a large tree of publication points, because you have to use customized software. Because publication points have very specific features, and it's not just a simple repository. And there is open source tools to do that. Actually, there's just one open source tool to do that, Krill. And you have to set it up. You have to make sure that it works, with self-signed certificates, because it was an isolated environment. We didn't want to put anything on the internet. We had to create major subtrees of 50 or 100 publication points for that. And then we had to install all the different relay and part implementations that were available at the time and make sure that they were compatible with this isolated tree, which again was not always something possible to do out of the box. We had to do some tweaking. And in the end, of course, there was a router, but the router we installed, I think, FRR routing software package to do all the comparisons of what the routers would receive at the end of these attacks. So installing the router itself was not the problem. It was just making sure that the entire RPKI infrastructure was working completely isolated from the actual transit anchors that it relies on.
Okay. I'm just totally curious because it's a whole nother world as internet level networking and protocols like BGP and those style of routers is very fascinating to me to build a lab and to mimic that, because these are not the same routers that people touch every day. These are not the same commands that you're using. So FR routing project, is that what you said?
FRR, yes. It's a routing software suite that at the time, I didn't want to wait until we could get our hands on a Cisco or a Uniper, because then there's a whole process to get to those resources. So I just went with FRR because it's open source. It's also used on the internet by a lot of people, even in production environments. So it's a good placeholder.
Got it. And Krill, you said, was the name of the software that does publication points? Yes, it's right now, really the only open source software that anyone can use to set up their own publication point for RPKI objects. Okay. But that's not the actual real software that's used for publication points, or is it?
It is. Okay. So there are a lot of entities that set up publication points. At the root are the 5 regional internet registries. And they, in general, have their own in-house implementations. But you don't have to necessarily use the service of a regional internet registry. You can also set up your own delegated publication point, and you just have to purchase resources from them. You have to create like an account with them, sort of to connect your publication point with them. But you can host your own. And if you're hosting your own, either you have to build something up from scratch from the RFC, or you use this open source implementation, which is very good, to be frank. So there is no reason to reinvent the wheel with it.
Oh, cool. So what do we do to prevent the downgrade attack?
To prevent it, well, that's a very good question. One of the things that you could do to prevent it is to make sure that it is impossible, more or less, to stall the process for so long, because the fact that you can stall it for so long is an issue in itself. So one way that you could do that is by, in a later paper, we propose the option of sort of creating a history of the different publication points that are on the internet. So for every single iteration, you have a history, how they behaved, how long does it take to process them. And when new things come into the system and they are behaving anomalously, you can tag them as such. When you tag publication points or repositories that are benign and some who are behaving in suspicious ways, you can prioritize or deprioritize them. And that's a way to sort of speed up the processing for all of the repositories that you know are behaving well, and those who are taking a very long time to process, you can just deprioritize. And also, you kind of would have to decouple the process of generating the data that you send over to the routers, which means you don't have to wait until the entire process is done to generate the new data and send it over, but also be able to do that also piecewise. Because if there is such stalling, in this way, you can make sure that new data is continuously fed to the router and it's not waiting for 8 hours or 10 hours until something expires and therefore becomes invalid.
That's really interesting. So this has been an awesome conversation. Thanks again for coming on the show. Appreciate it.